Good morning all. Do you have any questions from the previous class? Any questions? Okay. So we have derived the Euler's equation of motion for one dimension. So the Euler's equation of motion in one dimension. So we found that dou q by dou t plus q into dou q by dou s is equal to f minus 1 by rho into dou p by dou s. So this is the Euler's equation of motion in case of one dimension, right? Is this the one? Yeah, this is correct, right? Now the same thing. So if we expand the same thing for a case of three dimension, Avinash, what is the problem? I don't remember what was the question I have given yesterday. Okay, so you can post it in Telegram, so I will respond for that. Fine? Okay, fine. So this is for one dimension. So the same thing for three dimensional. So this will become del rather than dou, right? So this is dou q by dou t plus q dot del of q is equal to f minus 1 by rho into del p. So this is the Euler's equation of motion for 3D, right? So this dou by dou s becomes del. So that's the only difference, right? So wherever dou by dou s is coming into picture, so that we replace with del. Then actually we call this as the Euler's equation of motion in case of three dimension. So this is also called as Lamb's equation of motion. So Lamb's equation of motion. Now here, this component, right? So you might be aware what is q cross del cross. So what is q cross del cross q? Yeah, you need to remember derivation also. Yeah. So this is q cross del cross q. How much? What is the vector identity? What is the vector identity? So this is del of q dot q minus q dot del q. So this is the vector identity. Now if you bring this to this side and this to the other side, then this will be del of q dot q minus q cross del cross q, and this is equal to q dot del q. Now q dot del q can be replaced with this dou q by dou t dou q by dou t plus del of q dot q minus q cross del cross q is equal to f minus 1 by rho into del p. So this is q square. I think so. This is q dot q of, then this will be q square by 2 minus q cross del cross q. So this value dou q by dou t, this equation, so this value is equal to f minus 1 by rho into del p. So this equation is called as the Lamb's equation. This is what is called as the Lamb's equation. Got it? So in the Lamb's equation, so actually there was one question actually which was asked in the previous years of UPSC. So that is, what is the integral of Euler's equation? What is the integral of Euler's equation? So this question was asked, but the fundamental background behind that question is this one. So from this actually we are going to derive the equation of the Euler's equation. Yeah. Just a minute. This is glaring. Yeah, Lizu. So this is q square by 2. So in case of normal vectors, so I think actually, so in case of normal vectors, this is straightforwardly taken. But in case if the same vector is coming into picture, then this will be q dot q will be q square. Now when we take the derivative of that, there will be a 2 factor that comes into picture. So to compensate that 2, actually denominator 2 will come. Got it? So from this, actually, so we can derive the Euler's of equation of motion integration. I hope you noted down this. I'll just write it here. Dou q by dou t plus del of q square by 2 minus q cross del cross q is equal to f minus 1 by rho times of del p. Now here actually every letter is known. So q is nothing but the velocity potential, so velocity, and f is nothing but the force components, and then del is the operator and t is the time. So all these variables are known. Now here this del cross q is nothing but the rotational component. So this is the rotational component. Now I'll write this as dou q by dou t plus del of q square by 2 plus 1 by rho times of del p minus f is equal to q cross del cross q. So for a conservative force field, for a conservative force field, F can be expressed as minus del psi, some random function. Is this understood? Understood or not? What is a conservative force field in that case? You tell me what is a conservative force field. Anybody? Any idea? So in the textbook, he is using a different symbol, this symbol. Yeah. So conservative, we mean, suppose if it is not producing any rotational component, we call this as a conservative. That is, suppose if there is a block of mass here, on this there is a force here, there is a force here, and there is a force here. Now all the three forces together, it will try to rotate in one or the other direction. Got it? But rather than that, so this kind of forces all together we call as non-conservative. In case of conservative force field, what happens is there is only a specific direction of motion. So that is only linear motion. So any force or any set of forces which are causing non-rotating force, so that is a linear motion if it is causing, we call that as the conservative force field. Got it? Got it? So indirectly work done. Yeah, that's correct only. Indirectly. Why? Because the rotation, right? So here actually this will be a circular motion and linear motion will cause the work. Got it? The positional change from one location to another location as a block. So that is conservative force field. Now, so conservative force field, that is del cross F will be 0 definitely. So if del cross F is 0, then the vector identity del cross del omega is again equal to 0. So that's exactly the reason we can express F as minus del phi. As I told you, this negative sign is there will be a potential difference in the opposite direction. That's why we always take the reference as the negative. So that is minus del phi. And Q can be expressed as minus del phi. So these are the two important aspects which we are going to use it in Euler's equations integral. Right? Now here, if you replace it here, dou Q by dou T plus del of Q square by 2 plus 1 by rho del P minus F can be expressed as del of omega is equal to Q cross del cross Q. Now out of all these things, so this Q I can express as dou by dou T. So here also I will replace dou by dou T of minus del phi. So from this, if you take del out, so this will become minus dou phi by dou T plus Q square by 2 plus dP by rho plus omega is equal to Q cross del cross Q. I hope you understood why I have written this way. Understood or not? So is this correct? I have written dP by rho. When I took the del out, this del if I have taken out, then this will become dP by rho. So the reason being, rho may be a function of time or P may be a function of rho. So in such cases, what we will do is, without losing the accuracy, we will replace it with dP by rho and then integral of it. So this will take this del to the outside. So this is a little bit complex level of vector analysis, but it's completely the vector analysis, nothing more than that. So this is the final equation what we have got in the derivative format. So for an irrotational flow, this will become 0. Del cross Q equal to 0. So if this can be replaced with 0 and integrating on either sides, then this will become, del will cancel and the other side 0. The integration of 0 may be a function of time because you are doing integration with respect to the space. So the constant may be a function of time. So this can be replaced with minus dou phi by dou t plus q square by 2 plus integral dp by rho plus omega is equal to some random function of time. So this is ideally the constant. Constant we mean independent of space. Independent of space. Now this value you can, so both are functions of time. So if phi can accommodate this f of t, then you can straight away write as dou phi by dou t. I'll just write it here. Dou phi by dou t plus q square by 2 plus integral dp by rho plus omega is equal to constant. And this is the equation of motion for an irrotational unsteady flow. So there is a function of time. So that's why we call as unsteady. Here I have accommodated this negative sign and f of t into phi itself. So because this phi is a potential which we are going to calculate on the fly. So based on the arbitrary constants you are going to get the appropriate function, though we have accommodated negative sign and f of t together into phi. Got it? So that we are going to calculate on the fly. Understood? Any questions on this? So this was asked once by UPSC. What is the integral of Euler's equation? Any questions on this? But this is purely vector calculus simplification. This step you understood, Liju? F of t is independent of xyz. Yeah. So once you understand this f of t I have accommodated into this function of phi because this is a function of time. This is also a function of time. So this f of t and this negative sign I accommodated into phi itself. Phi may be a different function. So this phi I can replace with maybe capital phi, something like that. So this is capital phi became phi and f of t minus sign together. So this we are going to calculate on the fly. So because this is a potential we have defined in between, which is a scalar function. So this you have got the flexibility to keep it on your own. So that's why you can replace this entire functions together into a single function. Got it? Like the way arbitrary constant is there, right? So arbitrary constant, we don't put any number there. And then log c you are just accommodating as a c, or c you are accommodating as log c. The reason being the c will be calculated on the fly depending upon the initial conditions. So that's exactly the same reason what we are going to use here. Clear now, Liju? Okay. I hope it is noted down. So this is for the Euler's equation of motion for irrotational unsteady flow. Unsteady is nothing but derivative with respect to time. Irrotational is nothing but del cross q is equal to 0. So there is an unsteady component and then there is an irrotational component, right? Suppose if it is steady flow, then this will become, so q square by 2 plus integral dp by rho plus omega is equal to constant, and this part will become 0 because phi is independent of t. Got it? Is it noted? Okay. So two-dimensional motion. Two-dimensional motion. So this is the most easiest part of our syllabus, two-dimensional motion, and this is purely complex analysis, nothing more than that. So this entire topic is just based on complex analysis and only the applications of complex analysis. So two-dimensional motion, and this is the most important part of UPSC syllabus also. So most of the times, almost 70% of the cases, the questions were asked from this particular topic only, that is related to complex analysis. Clear? So here the two-dimensional motion we mean, suppose if there is a canal, in the canal if the water is moving like this, now at any plane, so if you take it, so the motion is happening only either x direction or y direction, or it may be both, but it is independent of the depth. So this is the z, so independent of depth. And this is what is called two-dimensional flow. Two-dimensional flow. Now, this two-dimensional flow is governed by the laws of complex potential. So, the complex potential usually we represent with W, and then if there is a velocity, and if Q del cross Q equal to 0, then Q can be expressed as minus del phi, and this is the base principle that we are going to use it, right? Q can be expressed as minus del phi if Q is irrotational. Then if this can be expressed as minus del phi, then this is nothing but Q is equal to I into minus of I into dou phi by dou x plus j into dou phi by dou y. So k component is not there. Why? Because we have ignored the completely one dimension, that is z component. So that's why this can even be expressed as minus dou phi by dou x minus j into dou phi by dou phi by dou y. So that means two-dimensional vector can be converted into a three-dimensional vector can be converted. This is a two-dimensional vector. So two-dimensional vector is nothing but a complex equation. So the complex equation, this part we call as the real, and this part we are call as imaginary. Right? So that's why this usually we express as minus dou phi by dou x minus I into dou phi by dou y. So this is how actually you can express it in the complex domain. These two are equivalent, and this is the reason why we rigorously use the complex analysis part in this equation, because we are specifically controlling our analysis only on two dimension. So that's why complex analysis became into important for it. Got it? Okay. So now there are two different aspects in case of complex analysis. Suppose if there is a function w which can be expressed as phi, then there exists at least one function that is almost perpendicular to phi always. So psi is perpendicular to phi, and this is what we are calling as the potential or velocity potential. So if there is a velocity potential, obviously there will be a flow, right? And this flow we call as the potential flow, and this potential flow direction that is getting represented with the help of the stream function. That means if there is a water flow like this, on this water flow, if there is an equipotential plane here, and if there is an equipotential plane here, and if the flow is in this direction, then this flow direction is represented by stream function. and these planes are equipotential planes. And this potential is the velocity potential. Got it? So W is equal to phi plus I psi. In that phi plus I psi, phi is the velocity potential and psi is the stream function. So this is the basic understanding you should be having it, and these things we will try to relate it here. Got it? So this is about the stream function. Just you note down, then actually we will bring out everything in the mathematical format. Note it down. Done. So here complex potential. So suppose if I call as F or W, whatever it may be. So F is equal to U plus, sorry, phi plus I psi, and then Q is equal to minus del phi, and this is minus dou phi by dou x minus dou phi by dou y dou phi by dou y into j, right? So this is a two-dimensional flow, so I am ignoring the k component. Now here this can be written as ui plus vj, or u is equal to minus dou phi by dou x and v is equal to minus dou phi by dou y. So these are the velocity components along the x direction and along the y direction. Now here if I take df by dz, sorry, df by dx, this is dou phi by dou x. So dou phi by dou x plus I times of dou phi by dou y. So this is based on the CR equations, or actually let me prove the CR equations first, right? So CR equations, what states is, so in case of complex analysis, we proved the CR equations, that is dou phi by dou x is equal to dou psi by dou y. This is one. And another equation is dou phi by dou y is equal to minus dou psi by dou x, right? So this is equation number 2. And same is the case even for the complex also. So that is f of z can be written as f of r e power I theta. Now if you take the derivative, so dou f by dou r is nothing but dou f by dou r is f dash into f dash of r e power I theta, and the derivative of the inner function with respect to r is e power I theta, and dou f by dou theta is nothing but f dash of r e power I theta into, so derivative of r e power I theta with respect to theta will be r into e power I theta into I. Now f dash r e power I theta into e power I theta can be replaced with dou f by dou r. So IR into dou f by dou r. So IR into dou f by dou r. So this is the CR equation. So this is equal to dou f by dou theta. Got it? So this one, so dou F by dou R can be written as, so because you can express phi plus I psi here, so dou by dou R of, and this will be equal to IR times of dou F by dou F by dou theta is equal to IR times of dou F by dou R, and dou F by dou theta, dou by dou theta of phi plus I psi is equal to IR times of dou by dou R of phi plus I psi, and this is dou phi by dou theta plus I times of dou psi by dou theta is equal to IR times of dou phi by dou R plus I times of dou psi by dou R, and this can be written as IR dou phi by dou R minus R dou psi by dou R. So if we equate the corresponding terms, dou phi by dou theta is equal to R dou phi by dou R, and dou psi by dou theta is equal to minus R dou psi by dou R. Minus R dou psi by dou theta dou R plus I times of R dou phi by dou R. So if we equate the corresponding terms, dou phi by dou theta is equal to minus R dou psi by dou theta dou R. This is equation number 1, and the second equation will be dou psi by dou theta is equal to R times of dou phi by dou R. This is equation number 2. So these are the two equations governing the Cauchy-Riemann equations. So these are called the Cauchy-Riemann equations in polar form. In polar, right? So this derivation, I left it in the complex analysis itself because I have clearly explained there. With the help of Taylor's expansion, I proved this. Got it? Here. So this is the CR equations, what we are going to use it. Now we will try to relate the fluid dynamics velocity potential. So these velocity components we will try to relate in this case here with the help of these CR equations. So that's why we just recapped the CR equations, whatever we learned there, and then we will try to apply now here. Yeah. So first you note down this. Note it down. Done. Now here the velocity components. So here actually in the two-dimensional flow, what we are interested in is finding out the velocity in the complex analysis. Now F is nothing but f phi plus I psi, df by dz is nothing but the derivative of the analytic function f. So this is dou phi by dou x plus I times of dou psi by dou x. So this is the derivative of the function in the complex domain, right? So this is the complex function f. So f is a function of z. So this derivative is nothing but the complex velocity. And this complex velocity you can find out. So dou phi by dou x is nothing but minus u, because this is dou phi by dou x is equal to minus u, and dou phi by dou y is equal to minus v. So this is dou psi by dou x. So as per Cauchy-Riemann equations, dou phi by dou x is equal to dou psi by dou y, and dou phi by dou y is equal to minus dou psi by dou x. Now dou psi by dou x you can replace with minus of dou phi by dou y, and minus of minus will be, this is, so this will come as plus v. So plus I times of v. So this is df by dz. This is what we call as the complex velocity. Now if you want to find out the magnitude of the complex velocity, we know that minus u plus iv into minus u minus iv, the product of these two will be a plus b into a minus b, that is a square plus b square, sorry, a square minus of iv whole square, and this will be u square plus v square. This is nothing but q square. So this is the velocity, right? Now this you can get it by taking the derivative of the conjugate function. This can be written as df by dz into df bar by dz, and this is what is given by u square plus v square, and the same thing you can express as q square, which is nothing but the square of the magnitude of the velocity. Square of the magnitude of the velocity, and psi is called the stream function. Here, from this analysis, whatever we have done till now, so we can conclude that first thing, q is expressed as minus del phi. So this is a potential flow. From this potential flow equations, so we have defined something called a complex potential. So complex potential involves both the potential function and the stream function. So this is the potential function and this is the stream function. Both will always be perpendicular to each other. So that's why you can express as phi plus I psi. Both are perpendicular to each other. This will be, so if you know this, the potential function, then you will be able to find out the stream function. If you know the stream function, you will be able to find out the potential function. This potential function can be used to find out the velocity here. So u is nothing but minus dou phi by dou x and v is minus dou phi by dou y. Now you can make use of those components directly to find out the velocity if you know the complex function in the form of phi plus I psi. So this is the complete information that's what we need in case of fluid dynamics analysis for a two-dimensional flow. Got it? So what we are interested to know is, one is what is the direction of the flow, that is nothing but the stream function, and another is what is the velocity components in the x direction and y direction, so that is nothing but a q. So these are the two important aspects what we are going to study. So both are known now. So with the help of complex analysis. Got it? Understood? And one more important aspect, that's what we are going to use is both phi and psi. Both phi and psi. So will satisfy the Laplace equation. I hope I don't need to prove this. This is known. So del square phi is equal to 0 and del square psi is equal to 0. So these two are called the Laplace equations for the potential function and the stream function. Both will satisfy that. So that's why these functions we also call as the harmonic functions. So any equation that will satisfy the Laplace equation we call as the harmonic equation. Got it? Understood? So this is the basic understanding we should be having it for the complex analysis to apply. here in fluid dynamics. Now, the applicability to the complex level. So, one part is, if you know the potential function, with the help of CR equations, you will be able to find out phi. The same examples of fluid dynamics we solved even in the complex analysis also, right? So, the same thing what we are going to do it here, but that is at lower standard now, because we already learned it. But little bit higher standard here it is. So there is a concept of source and sinks that comes into picture. So source and sinks in case of two-dimensional flow can be analyzed with the help of complex analysis again. So this complex potential, whatever we learn now, right? So this complex potential model, we can bring it up for a source and a sink, right? So that concept will make us very simple to analyze the fluid flow when there are presence of sources and sinks, right? So a source, we mean here, source is nothing but a place where the continuous water is producing there, or the fluid is getting produced from a single location, single point, we call as a source. For example, you take a bore well. So in the bore well, the water is continuously generated from one location, right? So it's continuously coming. But if you look at from the top of the ground, then there will be a continuous production of the water. We don't know where is the source. That is, it is coming from the ground. So that's what it is generating the water then and there itself. That's what we call as the source. So how we are modeling those sources? That's what we will be doing with the help of this complex analysis or the complex potential model. We can bring it up for a source. And the sink is nothing but a place where the water is getting drained up from a single point, right? So that is, suppose if you know, so if there is a well, then if the water is continuously flowing into the well, right? So that's what is nothing but the sink. So generation is the source and vanishing out is the sink. So if you look at from the top, so you feel that is completely vanished out. Got it or not? So that's just a feel for the analysis purpose. So in reality, it may not be there. Got it or not? So as per law of conservation of mass, so mass cannot be vanished out. But we are saying that mass is getting vanished at one particular location, right? So this is counter to the principle of physics. But still we will be assuming that the water is getting vanished there for our analysis purpose. The water is going into the bore well, that's it. Got it or not? So that is the concept of source and sinks. So in the sources and sinks concept, so by UPSC, all the times the questions that are going to ask are sources and sinks presence, and when the presence of source and sinks are there, how the stream functions are coming. So that is the only type of model you are expected. So in the UPSC, most of the times actually that is the kind of questions it was asked. Clear? So prior to that, we should be having this complex potential model, right? So this complex potential model, because a source can be modeled as a complex potential, a sink can be modeled as a complex potential. So with the help of complex analysis we are doing, and this is the basic understanding, you should be having it. Clear? Any questions on this? Any questions on this? Okay, fine. So that's all for today. So in the next class, I'm going to deal with the sources and sinks. From there, how we are bringing up the stream functions. So till then, yeah, good morning. Bye-bye.